What's up, guys? Alexander here with Date Psychology. I had a few requests to talk about effect sizes. So this is going to be a quick video about effect sizes in psychology. No math in this video. We're just going to go over the concepts, and this will be something that will help you, especially from a very basic level, a very introductory level, interpret effect sizes when you're reading papers, particularly papers in psychology, but generally any other papers that you will read as well. So a lot of the time when you read a result, if not in a paper, just in the media, that sort of a thing, it will say, they found a statistically significant result. So I have a video on statistical significance. See that. I'll try to put a link up. Statistical significance does not mean that something has meaning. It doesn't mean that something is what's called clinically significant or practically significant or meaningful, right? You can have a statistically significant result, but the effect is so small that in a practical sense, it is not meaningful. It's not practically meaningful. What we really want to know, what is actually the meat of a lot of results when we do detect an effect, is how big is that effect? What does that mean in practical terms? And that is where you have to look for measurements of effect size, which often you will not find reported in the media. If you're just reading an article about a study, for example, usually you will find it reported in a paper. Even though it's probably one of the most important data points that you can find in a paper, a lot of the time you won't even see it in the abstract. That's something that general movement in psychology is kind of trying to change right now. They're trying to focus more on effect sizes and reporting those as well as confidence intervals clearly. So basic primer here on effect sizes going forward. No math, so don't get too anxious. Here's an example, a visual example of an effect size, Cohen's d, which is one of the most common effect sizes. So you can have two results, both of them, let's say in this example, statistically significant. Yet you can see when comparing these two groups that one is much more different from the other group, right? In the first one, we have an effect size, Cohen's d of 2, which means that these groups are about 2 standard deviations away in the mean. The other is a Cohen's d of 0.3, which is the average effect size for psychology in general. If you take all of the papers in psychology, look at effect sizes, what is the average that you will see? It's about 0.3. And you can see in this that that's not a very large difference between the two groups. They overlap a bunch. So this is why effect size is very important, why there's something that you want to be looking for. Going on here now to the next slide. Cohen's d is an example of a standardized effect size, okay? We can think of effect sizes as two things, okay? Standardized and unstandardized. If you want an unstandardized effect size, you're looking at something that's in natural units, right? You're just taking the mean scores of two groups and subtracting one from another, and then you have an unstandardized effect size. Or you could be looking at something like regression coefficients. Let's look at some examples of what these are, and certainly you will encounter these. So unstandardized effect sizes will probably be pretty intuitive, especially if you're familiar with the scale being used. Let's use an example of a decile scale for physical attractiveness, right? A 1 through 10 scale, right? That's how we think of attractiveness in popular culture. We think about, oh, he's a 1, he's a 10, he's a 5. And so this is kind of an idea that we all have a good kind of mental barometer for, in a sense. Let's say we administer treatment to one group and it increases physical attractiveness by 5 points on a 1 through 10 scale. If I tell you that, you probably already have a good mental image of what that means, right? You go from the virgin to the Chad. Someone who is a 5 goes to a 10. Someone who is a 3 goes to a 7. So you see very, very big change, okay? So that's pretty intuitive. And looking at the unstandardized effect sizes, which are basically the raw measurements, what the scale tells you, right? The units from the scale that you're using, can be very, very informative. And you will actually want to look at this often alongside a standardized effect size to get an idea of what is going on there. Let's see, next one. Regression coefficients, not to be confused with the correlation coefficient, which we will also talk about. Regression coefficients are another example of a standardized effect size. And what is this? When you have a correlation between two variables, how much does one increase for the other? Here's a statistics website I took this image off of that gives you an idea of a regression coefficient and how to interpret that. So you get a result kind of like this, and you see how much variable y increases for a change in variable x. And it's using the natural unit. And the natural unit in this case is weight in kilograms and height in meters. So for every increase in height by 1 meter is associated with an increase in weight here by about 106 kilograms. Okay, so that seems like a lot, but we're talking about 1 meter increase in height. So kind of a measurement that you're not going to see in the real world, but that gives you an example. Another example would be something like education and income, right? You could say, okay, for every additional year of education, people earn $10,000 more on average. So you're looking at natural units here, right? The natural units being years of education and income in that case. So that's how you'll see correlations presented often. Again, it's an intuitive way to understand it because why? You know what weight is. You're already familiar with that unit. You know what kilograms are. You know what level of education means. You know what income means and that sort of thing. So let's go forward again. Okay. As mentioned, so in the former example, you have familiarity with the scale of 1 through 10 in physical attractiveness. Everyone has an idea, accurate or not, of what that might look like. What if it was a scale that you were less familiar with? What if I told you, for example, we have 2 groups. I give one group some kind of treatment, right? And this improves their scores by 53 milliseconds in the Stroop test, right? The Stroop test is a very common cognitive test with colors and words in cognitive psychology. Well, that might not be very meaningful. Is 53 milliseconds a large increase? Is it a small increase? What did the previous group have compared to 53 milliseconds? And that sort of a thing. This is when a standardized effect size might be more helpful in interpreting what is going on when you're not familiar with these units, or when the units, even if you are familiar with, maybe aren't as informative. Next slide here. You would need to have an idea already, right, of what to expect from Stroop test results. If you are a cognitive psychologist, if you're a neuroscientist, and you're working with this kind of experiment, you might have a good idea, right? You might say, okay, 53 milliseconds, that's a big, big improvement. If you've never heard of this before, do you know even what a normal response time would be? I don't, and this is certainly the kind of stuff that I have to read in school. So this is when you might want to start looking to see in a paper what effect size is reported, and is that a small, a medium, or a large effect. Next slide. And for that, we're looking at standardized effect sizes, okay? The feature of these is they're not using the natural units, okay? We're not comparing milliseconds, so to speak, or income or something like that. We're taking the units and we're converting them in a way that is standardized to make comparisons. And this is good because it lets you make comparisons sort of across studies, right? You can have 2 studies that compare kind of different things, or maybe it's a similar thing and they are using variables that are a little bit different, measures that are a little bit different, and then you get a standardized effect size that says, okay, I can compare this study with this study. And the general rule here is that it's broken down into kind of a convention where you say, okay, this is kind of a small effect size, this is a medium effect size, and this is a large effect size. Next slide here. Another example of a standardized effect size that you will see very often, perhaps the most common, is going to be a correlation coefficient. Specifically, Pearson's R is going to be a lot. When you see a paper that reports something like R equals 0.5, you know, that's going to be a correlation coefficient. That shows you the strength of one variable as it relates to another variable. How closely do the two conform along a line? This is something that's always going to fall between -1 and 1. That's not the case with Cohen's d or other effect sizes that compare means. It can fall along a larger area, but this is always going to be between -1 and 1. -1 being a perfect negative correlation, 1 being a perfect positive correlation, right? We see in the example here, this is a positive correlation at 0.5. If it were a negative correlation, it would be going down. But in either case, it's always going to be within that range of -1 to 1. Next slide. Cohen's d, okay, so this is just standardizing a comparison of means around the standard deviation, the pooled standard deviation. About 1 point difference in Cohen's d, well, I say about, it's 1 point difference in Cohen's d corresponds to a deviation by one standard deviation away from the mean of the comparison group. So it's a way to compare two means that is standardized. We kind of went over that in the other slide, so won't spend a lot of time on this one. So let's say that you read in a paper and it says, okay, the effect has a Cohen's d of 0.3. How do you even know if that's big or small? Kind of, you're in the same position as you were with the Stroop test and the milliseconds. If this is not something you're already familiar with, how do you even know? There are conventions, a general convention for interpreting Cohen's d. Okay. This is 0.2 small, 0.5 medium, and 0.8 is large. Now, I say this is a general convention. This is not a law or a rule. Moving to the next slide really quick here. You must be careful with these conventions. They can vary a lot by field. I mentioned the average effect size in psychology is 0.3. This may be different in other fields. There might be reasons for that. So typically the average effect that you see in psychology is going to be kind of small, both in a practical sense and as far as these conventions go. Why is that? Probably because one single variable is not actually that good at predicting human behavior, which is multivariate and very, very complex. But small effects may still be meaningful nonetheless, which we will look at in a minute here. So just because you see a small effect in a psychology paper, you don't want to immediately conclude that that effect is practically not meaningful. It might be, it might not be. Next slide. Here are some conventions for correlations, okay, for Pearson's R, right? We typically think of a small correlation as between 1 and 0.3, medium between 3 and 0.5, and then a large is anything above 0.5. So some examples here. What a correlation of 0.1 looks like, you know, pretty weak, and what one of 0.8 looks like, a bit stronger there. So, of course, if this was a negative correlation, it would be the same, just in the opposite direction. The conventions are still the same, right? Because you have that range of -1 to 1, with a 0 being no correlation at all. Next slide. Small effects, as I mentioned in the past slide, they can be very meaningful, even if they have a small effect size measurement in Cohen's d or something like that. Why is that? Let's use an example from epidemiology. This is a field that uses samples, often very, very, very large samples, if you're lucky, millions and millions of people. Imagine you have a very, very small effect. We'll talk about an unstandardized effect here, a practical effect. So we're talking about a 0.1 increase in mortality for people who eat green peas. That's not true, I just made that up, but for the example, you might think, okay, 0.1%, it's nothing for me. You know, that's a risk I'm perfectly willing to take. If you look at this at a population level, that amounts to about 33,000 additional deaths in the US every year from eating green peas. So you can have small effects on an individual level, or small effects in a standardized or unstandardized way, things that seem like a small number, but across very, very large populations, they may actually have a meaningful impact, which is often the case with risk factors for disease. Like I said, we're using an example from epidemiology. This is something that you'll see often, certainly with the pandemic and that sort of thing. Very small numbers, but you know, if this turns into something that affects the entire population, it can result in an absolute number of fatalities or whatever that's impactful for the population in that case. So the point is, don't immediately assume just because an effect seems to be small that the practical significance of that effect is low. It could be, often it will be, sometimes it also will not be. Next slide. Effect sizes. Everything we're doing in statistics are group statistics, right? We're not comparing individuals. We're comparing the means of two groups. And this is important because that means that there are limitations in what you can generalize from differences between groups to individuals. Strictly speaking, Making an assumption about an individual based on a group statistic is called the ecological fallacy. Often it will be wrong. In fact, when the group differences are very small, in a probabilistic sense, it will actually be wrong more often than correct. I have an article about that. Maybe I'll put a link up as well. So here in this slide is the sex difference from height. I looked up what this might be. I got some ranges from about a Cohen's d of 1.7 to 2. So about 2 standard deviations, the mean, away from the other group. You can see what this looks like here, where most men are taller than most women. Only about like 2 to 5% of men, if you look at this, are actually shorter than 50% of women. So yeah, most men taller than most women. This is a situation where if you were to look at this very, very large effect size and you were to generalize to individuals, you would probably be accurate most of the time, right? You could say that. You could say, you know, most men are taller. Let's look at another example in the next slide here. This is a sex difference for the big 5 trait of agreeableness. It's about 0.3, right? So the average of what we would see in psychology as well. You can see here that these two groups are very, very close. Okay, most men are still, you know, more agreeable, but only, or less, excuse me, less agreeable, but only slightly. If you were to pluck 2 individual data points out of these distributions, they could fall anywhere. There's no guarantee that a given man is going to be more or less agreeable. More often than not, that might not be the case. The differences are very, very small. And certainly in psychology, this is something we see with sex differences. Some differences are pretty large. Upper body strength, very large. Height, very large. If you look at cognitive abilities, I think visual spatial ability is one that's a fairly large cognitive difference. Many personality differences, many other cognitive differences, very, very small if they exist at all. And that's important because a lot of the time we talk about sex differences, the way that they're reported, and we try to apply them to everyone as if we have like these 2 independent groups that have no overlap at all, you know. Men are less agreeable, women are more agreeable. Okay, so true on average, but for individuals, a lot less true. It's not something that you want to generalize in a systematic way to most men or most women. Going on now to the next slide. There are other effect size statistics estimates out there. It's not just Pearson's R and Cohen's D. There are many, many more. Some of these have different conventions. So for example, partial eta squared here. If you look at these conventions, remember we had the conventions where it was like 0.3, 0.5, 0.8. Here we see 0.01, 0.06, and 0.14. So these are much, much smaller. If you're reading effect sizes in a paper, it's easy to get this wrong if you're used to seeing Cohen's D, which is actually, you know, what you're going to be used to seeing, because it's the most common thing. So you're used to seeing these in a paper. You might see, oh, 0.14, and you might immediately think, that's a small effect. Actually, it's a large effect if you're using this effect size estimate. There are others. I'm not going to go into them in any more detail because I want this to be a very basic kind of introductory video. Some effect size measurements don't even have very well agreed upon conventions. And interpreting those, you might be faced with the same limitations that you have when interpreting an unstandardized effect size. Next slide. An important thing to point out about effect size. Sample size, it impacts the effect sizes that you will see in the literature. Small samples will systematically produce inflated effect sizes across the body of research. Well, I'll explain why that is in a minute, but have a look at this graph here that kind of shows you, okay? So this shows you the average effect size for the sample size. The average effect size for studies in this, I think this was an analysis of papers in the field of education. The average effect size for samples that had fewer than 50 people was 0.44, so we're approaching a medium effect size. The average effect size for studies here that had a sample of over 2,000 people, 0.09, so a very, very small effect. And you really see a drop-off here at about 100 people, okay? At 100 people is when already these average effect sizes are about half of what they were, and you see an effect size of 0.22 in that case. So there's something going on with small samples that produce a systematic overestimation of effects in the research. This is kind of important. Let's go to the next slide. Large samples are able to detect smaller effects. And there is what's called publication bias. Journals, up until very recently, and I should say this is probably even still the case now, prefer to publish results that have a significant effect, right? A statistically significant effect. The larger your sample, the more likely you will have a significant effect if the effect is real. Why is that? Because large samples increase the power, which means the ability to detect an effect. If the effect is real but it is small, you need a larger sample. So larger samples will often produce smaller effects. Another thing going on here is that there's much higher variability in small samples when an effect is detected. So that means that small samples will often produce effects that are larger. The actual effect that is being detected, probably not that large. I mentioned, this is a systematic issue that occurs across the research. There are fields that use small samples almost always. An example is neuroscience, okay? Average sample size in neuroscience is about 20 people. If you read papers in neuroscience and cognitive psychology, you will often see very, very large effect sizes and very, very small sample sizes. If you were to conclude that, this field produces really strong effects, and compare it to something like social psychology, where you can often see samples of 500, 300 people, where you already see that big drop-off in effect sizes, and say, the effects are much smaller in this field, that would probably mislead you a little bit. We probably see larger effects in neuroscience in part because we're working with small sample sizes so often. Why small sample sizes in neuroscience, for example? It's much harder to get people to come into an fMRI machine. It's very expensive. You have to get them to come back the next day. Compare it to something like social psychology that uses a survey. You can put the survey up on the internet and you'll have 2,000 people that respond by the next day. So certainly it's a limitation when in a field, and this is something to consider depending on the field that you are in. You will eventually get an idea, a feel for what kind of effect sizes you expect to see within that field, and some of that will be related to sample size. If your field uses very, very small samples often, you're probably going to see a lot of very large effects in the paper. When I see very large effects in neuroscience now, coming from a background in social psychology, right, and going into neuroscience now, in the program that I'm in now, I don't know how to always interpret these effect sizes. I'll see sample size of 20. I can see, like a difference in milliseconds, like in the Stroop thing, and I think, okay, so that's actually, in a practical sense, kind of small, and then it'll be like effect size. Cohen's d 0.9. It's like, wow, that's a huge effect size. Something you don't see in psychology. Why is that? It might just be an artifact of the data, right? It might just be because this field systematically produces large effect sizes, and thus interpreting those effect sizes has to be done within the context of your field. So another point from this graph, right? You don't need a huge sample to attenuate this effect of inflating effect sizes. You see that it drops down pretty quickly already at about 100 people. Certainly that's something people get wrong a lot when they're reading papers, is they see a paper that actually has something that's actually considered a pretty large sample, let's say about 300 people, and they say, oh, that's such a small sample. Well, why do you think it's small? Because it feels intuitively small. Yeah, but that's the way statistics works, is you can take samples that seem fairly small, right, and generalize them to very, very large populations. A sample size of about 1,000 people, for example, can generalize to the whole US population with a margin of error of about 2 to 3%. So certainly there's something going on there that people don't always grasp intuitively, is that numbers that seem small relative to a very, very large population are still often pretty sufficient when selecting a sample. But you kind of got to get a feel for where that is going to be and how it will affect your effect sizes. Let's go on now to the next slide. There are some big limitations with these effect size conventions. Some of this you may have intuited from the previous slides, right? You get these conventions, small, medium, big, at 0.3, 0.5, and 0.8. And it's not a law. It's something that we made up in a way. Cohen, who came up with this effect size calculation, he would later go on to criticize this and say, I wish I hadn't said these conventions. If I remember the history correctly here, I think he didn't even want to originally give kind of a guideline for effect size conventions, because just following that rule is, as you would see in the neuroscience example, it could mislead you a lot. And in the epidemiology example, it could make you think that an effect is not meaningful because it has a small effect size, standardized, when in fact it actually is meaningful, particularly on a population level, but it could even be meaningful on a smaller population level or on an individual level in that case. So where does that leave you at the end? You have to kind of be familiar with the research related to the specific field that you're in and that you're studying to know for sure how meaningful an effect size is, right? And this is not something that can be done easily overnight, because it means, reading a lot of papers within your field, seeing what kind of effect sizes come from different measurements, different psychometric devices, the tests that you're doing or whatever, kind of getting an idea of where those results compare to similar results from replications, similar results from non-replications, but similar experiments from similar topics covered and that sort of thing. And that means that understanding how meaningful they are, and that is kind of a journey that you will pick up eventually. The more that you read, the more papers that you read, the more you go through the methodology and the results and you look at the actual numbers, right? And you get a feel for what you should expect to see when an effect is big and when one is large. For the meantime, if you're just starting out reading papers, you're a new psychology student or whatever, then the conventions are a good place to start, right? They will give you an idea, of what is normal within psychology. Like I mentioned, average effect size in psychology, 0.3. So some people have said, we should actually shift these conventions in psychology kind of to the left, right? If the average effect size in psychology is 0.3, maybe we should say a small effect is a 0.1 and a medium is a 0.3 and a large is anything over a 0.5, okay? So certainly that's one way to interpret them, and that's an interpretation that is relevant, or I should say that is relative to results as you generally see them in psychology, right? You say something is large, and so the question is, large compared to what? In this case, it would be large compared to past results in psychology. And a better, a more specific way to do that, as I mentioned, would be to get very, very familiar with the devices being used when you measure something. And when I say devices in something like social psychology, I'm talking about surveys, right? I'm talking about the tests, the personality tests that you give. If you're in like cognitive psychology, neuroscience, the tests on the computers that you give to people, the Stroop test, that sort of thing. If you're studying intelligence, something like an intelligence test, and understanding what those differences mean across the research in time. So an introduction to effect sizes. Certainly there's much more in more detail that I haven't covered, but I wanted this to be a introduction, a very general introduction of, if you're going into this for the first time, you're a student, you're reading papers, and you want to know what to look for, and if a result is meaningful. Effect sizes are one of the first things you should be looking through in the results. Now you have an idea of some beginning conventions for how to interpret effect sizes, right? Cohen's d, 0.3, 0.5, 0.8, different alternative psychology interpretation, 0.1, 0.3, the average, 0.5 for large. And now you also know some of the big limitations and where to go forward from that as you continue to read, study, research, and progress through your career in psychology. So, hope you guys enjoyed the video. I'll try to make another for you very soon.